In today's class, we're going to continue our discussion of gases. In a previous class, we considered some calculations involving the ideal gas equation. And in today's class, we're going to extend our understanding of ideal gases and look at other topics such as mixtures, the kinetic molecular theory of gases, and aspects of particle motion, including fusion. To review from last time, at STP, that means standard temperature and pressure, how does an equal volume of helium differ from nitrogen? Would they be identical in all respects since they're ideal, have different density, have different average kinetic energy? What's your reasoning? Can you explain it? We saw last time that if we use the expression PV equals nRT describing an ideal gas, that if we are at standard temperature and pressure, 1 atmosphere, 0 degrees Celsius, that at standard temperature and pressure they would have an equal volume, and that would be corresponding to the same number of particles, the same number of helium or nitrogen, and that resulting volume would be 22.4 liters. They would have different density, however, because even though they have the same number of particles, those particles have a different mass. It's the number of gas particles that affects a property like the pressure. If they have different mass, they would have a different density. In today's class, we're going to consider if there's other gas properties that are also affected by the mass besides the density. That idea of the average kinetic energy, they have different average kinetic energy because it turns out the average kinetic energy, that's what the temperature is measuring. In this case, they have the same average kinetic energy because they are at the same temperature for our standard temperature and pressure. So the idea that the average kinetic energy is what the temperature measures, that's something we'll explore in today's class. The first topic is looking at a mixture of gases. Let's say we have gas A that's in this cylinder that has a pressure of 0.6 atmospheres. We have a second cylinder with a gas B with a pressure of 0.4 atmospheres. If those were put together into the same volume of cylinder here, we could simply add together the pressures, 0.6 and 0.4, to add up to 1 atmosphere. That's what this expression here at the top is saying. The total pressure is due to the pressure of the subcomponents that we have. Subcomponents being gas A and gas B. Those are exerting what are called a partial pressure. Gas A had a pressure of 0.6, gas B 0.4. Those are the partial pressures. If we add it together, we get the total pressure. This expression here at the bottom is going to be useful as we think about those. This symbol here, chi, is for the mole fraction of gas component A. The mole fraction would be to say what is the amount of that we have of A over the total amount. The moles of A divided by the total amount, that would be the fraction of the total mixture that is coming from A. Let me show you how that's useful. So consider this question. The words at the top are setting up the same thing that are in the image. We're combining gas A and gas B and putting them in the same container. 0.6 atmospheres, 0.4 atmospheres put together equals 1. And the question is, how many moles of gas A and how many moles of gas B would be in that green cylinder? We have a description of the volume and the temperature and the pressure, so we could use PV equals nRT. We could put it all together and find the total number of moles of gas that are in the green cylinder. Then we could look and say that 60% of the pressure was coming from gas A. I'm getting that because its partial pressure is 0.6 and the total is 1. That's 60%. 40% of the pressure is from B. If we were putting that together, 60% of the gas particles must be from A and 40% must be from B. Since we know the total number of moles of gas, we can just use 60% and 40% to come up with each of the portions there. I'm taking the total number of moles, seeing how much it's contributing based on its partial pressure to get how many moles are in the container. Here's a related problem. I'd like you to give this one a try. We have a description of a mixture of 3 different gases. we have a volume for the container and its temperature. And the question asks us to calculate the partial pressure of each of the gases in the mixture and the total pressure. Give that a try. My first step would be to figure out what would be the total pressure. We can add up the mole amounts for each of the provided gases to get the total number. Put that into a PV equals nRT expression to figure out what the total pressure is. Then, what would be the contribution from each of the different components? Well, I could see how many moles of each of the gases I have relative to the total number. This is getting the mole fraction. The mole fraction times the total pressure. This would be giving me the partial pressure of each one. Now, we've been discussing the ideal gas law, PV equals nRT. A law that's describing some observations that have been observed and confirmed again and again. Different gases are consistent with this expression. If you vary the pressure, vary the temperature, vary the volume, this equation seems valid again and again in a lot of different scenarios. But why is it working? Why are these relationships valid? In order to explain it, we need a theory. A scientific law is describing a set of observations, and a theory seeks to explain those. We're going to use the kinetic molecular theory of gases to explain the ideal gas equation. Here are the different components to that. Okay, we want to be able to understand these, see when they're valid or not, and how they are leading to our ideal gas equation. So, first of all, gases consist of a large number of molecules, and that if we think about the volume of the container, most of it's empty space. That's what's being shown in this image right here. This image is consistent with the kinetic molecular theory of gases. Let's think about their particle motion, okay? So within this one, we're going to look at a simulation to look at the ideal gas consistent with the kinetic molecular theory, and we want to think about aspects of its motion. So what I'd like you to do is, when the gas particles enter the chamber here, try to focus on a single particle. Try to track it as it moves throughout the chamber. And consider whether the trajectory of your particle, is it straight or is it curved? And what happens when it strikes another particle or the wall? Particles will be added. Try to pick one and track its motion. If you lose your particle, choose a different one. So how did you do? I did pretty well following the trajectory of my particle. As I looked at it, it was always traveling in a straight line. When it says that the gases are in random motion, that random motion includes the particles moving in straight lines, not curved. That's related to this component. Attractive and repulsive forces are negligible. Gas molecules exert no force on each other unless they collide. If there was a force that was acting between them, their trajectories would be arced. As it approached another one, it would be a curved trajectory, and that's not taking place. They're always in straight lines because there is no attraction or repulsion unless they collide. Within the collision, the motion changes. We have a transfer of energy between the particles, or it could exert pressure on the wall. Gas molecules, again, are going to exert no force unless they collide. Those particular collisions are perfectly elastic, meaning the energy is transferred, but it doesn't decrease along the way. If it was to decrease along the way, over time, all of your gas molecules there would be sitting at the bottom of the container as they've lost their energy, and that doesn't take place. And the pressure, that's what's being caused by the collision of the gas molecules with the walls of the container. Now, this idea of attractive and repulsive forces are negligible. When might attractions be significant? Well, if the temperature of the gas is quite low, if the particles are quite close together, under these conditions, the attractive forces could begin to emerge. So this leads us to an important conclusion. When would a gas behave most ideal? It's when the gas pressure is low and the temperature is high, because under those conditions, the attractive forces are not present. Now, we could begin to deviate from that. A gas could behave more in a real rather than in an ideal sense if the pressure is high or the temperature is low. And that's something we'll explore later in the chapter. I'd like you to make some predictions here. What will happen when we have our gas particles in the chamber and heat is added or removed? What will happen to the particle motion, the temperature, and the pressure gauge? Take a second, share your predictions. Here we have our particles moving around. We add heat, thermometer goes up, particle motion increases, and the pressure increases. More frequently striking the walls of the container with greater force. We remove heat, thermometer goes down, the average kinetic energy of the particles decreases. Now, if you are tracking a particle, was your particular particle a fast particle, a slow particle, or both? When I track it, I find that it's both fast and slow. A given particle, sometimes it's moving fast, sometimes it's moving slow, and we see that it changes as different collisions are taking place. That's shown here in this particular simulation. We've now added histograms to look at the kinetic energy and the speed. As the particle motion decreases, the thermometer goes down, and notice the histograms get pushed over towards the left-hand side there. Very little particle motion. As the particle motion increases, the average kinetic energy goes up, thermometer goes up, and now the distributions are shifted more to the right-hand side. Those particular histograms, that's what's shown in this image right here from the e-text. This is showing how when you are measuring the temperature, you're measuring the average kinetic energy of the particles in motion. Higher temperature, the profile shifts to higher values. Time for another prediction. Here we have 60 heavy gas particles in the container. We see that they're at a particular temperature and they're exerting a particular pressure. What's going to happen when we now add 60 light particles? So we'll have 60 heavy and 60 light. What will happen when we add the light particles to the chamber, ones with a smaller mass? Would the pressure remain constant, increase a little, double, or triple? It's going to double here. That comes back to our idea of partial pressures. We could use PV equals nRT for the first 60 particles, PV equals nRT for the second. We've doubled the number of particles, so we've doubled the pressure. The total pressure, remember, is the sum of the partial pressures that are involved. And the partial pressure depends on the amount, the number of moles of each gas. Now, what about the particle motion? Will there be any differences? We see that the total pressure has doubled because we've doubled the number of the particles. Will the motion of a light particle be identical to the motion of a heavy particle? Let's use the sim to explore it. So we're going to start out by adding the heavier particles to the chamber. We've seen this a couple times, so we're familiar with what their particle motion looks like. And the thermometer is a measure of their average kinetic energy as they're moving through space. Here are the light particles. I see similarities, but a big difference is these are a lot more difficult to track. Okay? The velocity with which they were moving was much greater. So I see that there are similarities in terms of the particle motion, but it was a lot more difficult to track the particles when they were lighter. What was going on there? If we look at these profiles, we could consider them to be reflecting aspects of the temperature, where the higher speeds corresponded to the higher temperature. If the temperature was the same but the masses were different, this would be the data. We see the same kind of profiles being shifted to the right, but we see the ones that have the smaller molar mass have a higher speed. Why do they have a higher speed? We said that the thermometer is telling us the average kinetic energy. If the particles have a smaller mass, the only way they can have the same average kinetic energy, they have to have a larger velocity. So that's why we see that the lighter particles have higher speeds. The smaller mass particles, in order to reach the same kinetic energy, have to be moving around more rapidly. The smaller mass particles will be striking the walls of the container more frequently. And that's how they end up exerting the same pressure. Now, what would happen if we have a hole in the container? So we'll put a small hole at the top. The particles can now leave the chamber, and we see that the lighter particles are more frequently leaving the chamber. They're striking the walls more frequently, and if they happen to strike the spot where we have an opening, they can leave the container. That leads us to our next topic, when we're looking at effusion. On the right-hand side, that scenario is set up. We have the particles of gas moving around and a small hole in the container. If a particle strikes that particular area, it can leave the chamber. And because our lighter particles are bouncing around the chamber more rapidly, they have a better chance, a higher probability of striking that particular area. That results in different rates of effusion being this particular process right here. So this shows in relative terms the rate of effusion for two different gases. Higher rate means it's leaving the chamber more rapidly. We have the rate of effusion for gas 1 over gas 2 being equal to the square root, and then notice how their molar masses are inverted. They're inverted because this reflects how a molecule with a smaller mass will have a higher rate of effusion. This is said to be illustrated with this image right here. How does this image illustrate Graham's law of effusion? Try to put it into your own words and offer an explanation. To finish up, this is a way that this particular topic and the topics that we've looked at in today's class session can appear on a test. This one shows 3 different particle representations. Same size volume container, but different amounts of helium and nitrogen gas. And you're asked to rank these samples from smallest to largest in terms of the total pressure, the partial pressure of helium, the density, and the average kinetic energy. Within this, they have the same volume and they're at the same temperature. This particular format, this is easily placed onto an exam because we could use an image like this and set this up in a multiple choice format. So give this one a try. If these particular containers have the same volume and same temperature, but different numbers of the particles, try to do these particular rankings and share your work.